Welcome back, class. On this new topic, we're going to now be talking about working with non-right angle vectors. Everything we've done so far has been at right angles with each other. That means it's traveling north, east, south, or west, or that they're at a 90-degree angle with each other. So now it's a little bit different. By the end of this, you're going to have to be able to add non-perpendicular, non-parallel vectors by finding and adding components, drawing head-to-tail diagrams, and determining the resulting graphically or algebraically. In our first example, we are given a student walking at 105 meters south, turning and walking 87 meters at 64 degrees south of east. We want to determine what is the student's displacement. Now normally this would be a pretty straightforward question from what we've been doing, because he's heading south, but then when he turns, he's now going 64 degrees south of east. This is where it starts to get a little trickier. To solve these problems, we have 6 steps, which sounds like a lot, but it's not very bad once you break it down. It's very similar to what we've been doing, just again a few more steps. So our first step tells us to draw each vector separately, including the horizontal and vertical components. So in our first displacement, or on his first leg of the walk, he travels 105 meters south. So that displacement 1 is equal to 105 meters south. He's just going in the one direction. After he turns and he walks 87 meters at 64 degrees south of east. So his second leg of the walk is something like that. We're going to call that displacement 2 is equal to 87 meters. Now it tells us to, after we draw each vector separately, we need to include the horizontal and vertical components. Now if we look at the first displacement, we have no horizontal component. It's going straight down, or it's completely vertical. The second displacement though is a little different. We are going to have a horizontal component, which I'm going to label as displacement 2x, and we are going to have a vertical component, which I'm going to label as displacement 2y. We also were given that he is traveling at 64 degrees south of east. That means that angle right there is equal to 64 degrees. So to determine our x and y components of each vector given in the problem, on our first one, again, we have no x component. It does not move horizontally at all. So d1x is equal to 0 meters. Now its y component is d1y, but again, that is just 150 meters. But I'm going to determine which directions I want to make positive and negative. In this question, I'm going to make north positive and east positive, meaning south's negative and west is negative. So because we're traveling south, our displacement in the the vertical direction is negative 105 meters. Remember, this negative just talks about the direction we are going. We're going south. In displacement 2, we have a little bit more work to do. We are given a hypotenuse and we are given an angle. Remember, we have our trigonometry rule that we can use that we've called SOHCAHTOA, meaning that we are going to use sine if we have the opposite and the hypotenuse, cosine if we have the adjacent and the hypotenuse, and tangent if we have the opposite and the adjacent. So for this one, if we are solving for its horizontal component, we are wanting to find what is adjacent to 64 degrees, and we are given the hypotenuse. So when we're using adjacent and hypotenuse, we're going to use cosine. So the cosine of 64 degrees is equal to its displacement in the x direction divided by 87 meters. It's equal to the adjacent over the hypotenuse. The adjacent over the hypotenuse. So when we rearrange this and solve for d2x, we want to get that by itself. So we're going to multiply both sides by 87 meters. If I rewrite that, displacement in the x direction is equal to 87 meters times the cosine of 64 degrees. When you plug that in and solve, you're going to calculate an answer of 38.1 meters. Now we also want to determine the y direction, or the vertical direction. So this time, using the 64 degrees, we have the opposite in the hypotenuse, meaning we have the opposite in the hypotenuse. We're going to use the sine of 64 degrees. So the sine of 64 degrees is equal to the opposite, which is d2y, divided by the hypotenuse, 87 meters. Again, you rearrange the same way. So your y component is going to be equal to 87 meters times the sine of 64 degrees, which is going to give you an answer of negative 78.2 meters. Again, it makes sense that the answer is negative because we are heading south, and in our direction we determined that south was negative. After we're done our first two steps, our third step tells you to add all of the components in the x direction. So for our first displacement, or when he's heading south, there is no x component. So we are going to have dx is equal to its first component, which is 0 meters, plus its second horizontal component, which is 38.1 meters. So our x component is equal to 38.1 meters, our total x component. We can now do the same thing for our total y component. Our total y component is equal to the total from the first component, which is negative 105 meters. Negative 105 meters, plus our second displacement, negative 78.2 meters. Negative 78.2 meters. When you add those together, your displacement vertically is 183.2 meters. So what we did is we took both components and now we're combining them to make just one component. This is our total horizontal distance traveled. This is our total vertical distance traveled. We can take this to determine our total distance travel by creating a new vector addition diagram. So in this vector addition diagram, our horizontal component, again, is going to be 38.1 meters. Our vertical component is going to be 183.2 meters, and that will allow us to find our total displacement. Our total displacement. Remember, displacement's a vector, so we also need to have a direction, which we are going to use that angle to find. From here, it's straightforward and exactly what we've been doing. We're going to use Pythagorean's theorem to solve for d, or displacement, so that's equal to the square root of 38.1 meters squared plus 183.2 meters squared. When you calculate and solve, you'll determine that it's 187 meters. And Again, we need to find what angle we are traveling at. So to do that, we are given the opposite and the adjacent, which means we're going to use tangent. So the inverse tan is equal to the opposite, 183.2 meters south, divided by the adjacent, 38.1 meters east. That will give us a final direction of 78.3 degrees south of east. South of east. So our total displacement is going to be 187 meters at 78.3 degrees south of east. Again, what we did is each step at a time, we calculated the horizontal and vertical components of each leg of the trip. We used those to combine to make a new vector addition diagram of the whole trip and solve the same way.